Hey guys, welcome back to another lecture video for Chem 115. Now, for the majority of the lecture videos we've covered thus far for chemical equilibrium, we've been representing the mass action expression for the equilibrium constant Kc as the ratio between the concentration of the products raised to its own coefficient divided by the concentration of the reactants raised to its own coefficient. So this mass action expression, utilizing concentration units, can be applied to both aqueous and gas phase reactions. So in this lecture video, we are going to learn how to express the equilibrium by utilizing not concentration as the unit to represent amount, rather partial pressure. So let's go ahead and get started. And so when we're discussing the equilibrium constant for gases, there's going to be two different types. And it just really depends on the unit of amount that we're using. And so if we are utilizing concentration, then we're going to express that equilibrium as Kc. However, concentration or molarity is not the only unit to describe the amount of substance that's present per given volume. For gases, we can also utilize partial pressures as the unit to describe the amount of substance in that specific container. And so we're going to go ahead and take a look at why we can go ahead and do so. So if we start with the ideal gas law, PV equals nRT, we're going to go ahead and divide V to the other side. And we're going to group the volume with that of moles. And so N over V represents M, capital M. And capital M represents molarity. And so it looks like the pressure is proportional to the concentration, and R and T, we're going to treat it as a constant. Okay. And so the main idea here is that the pressure of a gas is proportional to its concentration. And so that's going to lead us to express the equilibrium constant a little bit differently when we use partial pressure in place of concentration unit. And so when we're utilizing partial pressures to represent the amount, the unit that these partial pressures are going to be at is going to be atmospheres, or ATM. And so gases can also be described by using their partial pressures in a mass action expression, such that if we have this chemical reaction, the partial pressure of ammonia over the partial pressure of the two reactants, which is N2 and H2 gas, is equal to the equilibrium constant Kp, where P is going to signify to the audience or the reader that the unit is in partial pressure units, not concentration units. And so this P, once again, is going to signify that the unit in the mass action expression is going to be partial pressure. And not concentration. Okay. And so I want to go ahead and rewrite this mass action expression. So the mass action expression for Kp is simply going to be the partial pressure of the products, which in this case is going to be NH3, raised to its own coefficient. So notice that here we have a coefficient of 2, so therefore it's going to be raised to the second power. And then we're going to divide that by the partial pressure of the reactants. In this case, it's going to be nitrogen gas raised to the first power because we have a 1 as the coefficient, times that by the partial pressure of hydrogen gas. And notice that we have a coefficient of 3, and so therefore, I'm going to swing this over here. It's going to be raised to the third power. And so overall, we still have the same format for a mass action expression. However, the unit is, in this case, is going to be the partial pressure instead of concentration. So partial pressure of the products over partial pressure of the reactants. And I'll just go ahead and duplicate this. And so if you guys haven't seen this notation before in the first semester of general chemistry, the partial pressure is symbolized as capital P. And then this, the subscript that follows, for example, N2, represents the identity of the gas. Okay. All right, so what we're going to do is we're just going to quickly review the idea of partial pressures. And so let's just say that we have a pure sample of oxygen gas that's in its own container. And then we're going to go ahead and add it to a container that's filled with nitrogen. And so what we get is this mixture of these two gases. So we have this container that has a mixture of two gases. And so we can go ahead and summarize the total pressure of those gases as simply the sum of the partial pressures. So PO2 plus PN2 is equal to the total pressure. So these are, so it's the sum of partial pressures. Okay. And so P total can be represented as P with a sub T. And if you recall from the first semester of general chemistry, you guys can figure out the partial pressure. So all of this is going to be representing the partial pressure. Let me see if I can write this just a little bit more neatly. Okay. So partial pressure of those gases. Okay. And so the partial pressure of these gases can be calculated by determining their mole fraction, which is this whole piece right here. And so the symbol for mole fraction is this chi, and then the identity of the substance, which is represented by that subscript. And so if we take the mole fraction and we multiply it by the total pressure, that's going to give us the partial pressure of that specific gas. And so this is what you guys learned in the first semester of general chemistry. However, we can also calculate the partial pressure in a different way, in a different manner. And so if you guys recall, PV equals nRT can be written as, put these two together, so pressure is equal to the concentration times that by R times that by T. And so this R value is going to be 0.0821 liters, atmospheres, moles Kelvin, and the unit for temperature is going to be in Kelvin. Okay, and so we can express the partial pressure by utilizing this formula. And so if we are not given the total pressure of the system, we need some way to calculate the partial pressure. And we can go ahead and do so by utilizing PV equals nRT, this modified form of PV equals nRT. And so, oops, wrong arrow. So overall, we can express the partial pressure for gas A if it equals to the molarity of gas A times this by R times that by T, or the partial pressure of B if we know the concentration of B and we multiply it by R and multiply it by T, or the partial pressure of C if we know its concentration and we multiply it by R, multiply it by T. And so this gives us a flexibility, if you will, to calculate the partial pressures if we know the concentration of the gas. So let me just go ahead and write this real quick. Give me a second. So this is going to represent the partial pressure. And this is going to represent the concentration. And so this is cool because now we have an alternative way of calculating partial pressure if we know the concentration, or vice versa. We can calculate the concentration of that specific gas if we know its partial pressure. And then we'll just divide RT to the other side. And so because there's a relationship between partial pressure and concentration, there's also a relationship between the equilibrium constant when it's expressed in terms of partial pressure and the equilibrium constant when it's expressed in terms of concentration or molarity units. And so this is the formula where Kp is the equilibrium constant under partial pressure, Kc is the equilibrium constant for concentration units, R is going to be 0.0821. Now when you're using this form, when you guys are using this equation, the unit for R does not, it's not going to be liters times atmospheres divided by mole Kelvin, it's going to be 1 over K. And so we're going to go ahead and simply cross this out to serve as a reminder that the unit for R in this equation is going to be 1 over K, or 1 over Kelvin. Okay. And so T is going to be temperature, it's going to be in Kelvin units. And last but not least, here we see delta N. So delta N is the change in the moles of gases. And so typically it's final minus initial. And so we can think about this as the final state, the product is the final state, and the reactant is the initial state. And so please remember that we're talking about moles of gases here, gas being the identity of the substance. All right, So let's go ahead and apply this equation to a problem. And so we're first going to consider this chemical reaction. And if Kp turns out to be this value, then what is the value for Kc? So there's two things I want to do before we actually address this question. First, because Kp is an equilibrium constant, notice that this value is unitless. Okay, so Kp, much like Kc, is going to be unitless. Okay. And so just for kicks, I want to go ahead and write the mass action expression for this specific equilibrium, just to get some practice. And so the mass action expression for Kp is simply going to be the partial pressure of the product. So the product is going to be N2O4, dinitrogen tetroxide. And in this case, this partial pressure is raised to the first power. Divide this by the partial pressure of nitrogen dioxide raised to the second power. So this is just for practice. It really doesn't have anything to do with the problem. Okay. All right, so now that we got those 2 points out of the way, let's go ahead and actually work on this problem. So we know that Kp is equal to this whole stuff, so I'm just going to go ahead and write that. So Kp is equal to Kc times this by R times this by T. And it was, so this part right here, so this, well, let me just erase that then. This part right here is going to be raised to delta N. And so I know that the value of Kp is going to be 0.480 because that's given to me. And the question is asking us to determine the value for Kc at the same temperature. And so Kc is going to be my unknown. I know that my R is going to be 0.0821. 1 per Kelvin, that's my unit. Times this by temperature. And so temperature needs to be in Kelvin. And so you need to add, so it's going to be 25 degrees Celsius plus 273.15. So this is going to be 298.15 Kelvin. Notice how the K's will cancel, raise that to delta N. And so let's go ahead and figure out the change in N, delta N, which is representing the moles of the gas in the product side minus the moles of the gas in the reactant side. And so we can go ahead and take the coefficient to represent the number of moles of gas in this, from this balanced chemical equation. And so it's going to be 1 minus 2. Okay, so this is going to represent the product, the coefficient, let's just write coefficient here, of the product and coefficient of the reactant. So the coefficient of the product and the reactant can represent the moles of gases. And so it turns out that delta N is going to be -1. And so we're going to go ahead and rewrite this whole thing. So 0.480 is equal to Kc parentheses 0.0821, 1 over Kelvin, times this by 298.15 Kelvin raised to the -1 power. And so I'm going to solve for Kc. So I'm going to go ahead and duplicate this, and I'm running out of room. That's okay. So Kc, so what I'm going to do now is I'm going to take this guy and I'm going to move it to the other side. Okay. Do I have room? Yeah, I do. All right. So what I did is I divided everything to the other side, and now that everything is solved with respect to Kc, all the terms are moved, isolating Kc. I'm going to go ahead and plug this into my calculator. So 0.480, divide this by 0.0821, times that by 298.15. And so the value that I get for Kc is going to be 1.96 times 10 to the negative 2. And so remember that Kc is unitless. Now another way that you guys can express this answer is moving the decimal place 2 places to the left. So this is going to be 0.0196. Okay? And that's an equal value for Kc. So you guys can represent the answer in one of two ways. All right, so pretty simple enough. You just plug and chug. The only tricky thing here is, I guess, identifying the numbers that you're going to be using for the moles of gases. But here it's pretty straightforward. You guys just use the coefficient of the product, and you subtract that by the coefficient of the reactant. So I'm just going to go ahead and move this piece right here, and I'm just going to go ahead and box this just so you know it's separate from my actual work that's related to this problem. All right, so we're going to go ahead and look at one more example. We're going to go ahead and solve for Kp this time if we're given Kc as well as the temperature. And so for this example, very similar to the first, I want to go ahead and get some practice in terms of writing the mass action expression for Kp. So the mass action expression for Kp is equal to the partial pressure of C raised to the fourth power. Divide this by the partial pressure of A raised to the first power, times this by the partial pressure of B raised to the second power. So if I ask you guys to write the mass action expression for Kp for this reaction that involves these gases, you should be able to know how to do so. And so once again, this is just for practice. Really has nothing to do with the problem. Cool. So recalling the equation, we have Kp is equal to Kc, parentheses R times T raised to the difference in the number of moles of gases. Only thing that we have to do here is just plug in our given values. So Kc is 0.990. That's easy enough. R, I'm just going to go ahead and kind of move this over to this side. Let me zoom in. So this is going to be 0.990. And then R is going to be 0.0821. And the unit is going to be 1 per Kelvin. Now, the temperature is 25 degrees Celsius. You're going to add 273.15. And so what we get is 298.15. and this is raised to the delta n. And so the change in the number of moles of gases can be calculated by taking the difference between the coefficients of the product and that of the reactants. And so here, in this case for products, we have 4 moles. For reactants, notice that we have A and B. So if this is 1, 1 plus 2 is 3. So we have 3 moles of reactant particles. And so the change in N is simply positive 1. And if we were to plug that into our equation, Kp is equal to 0.990 parentheses 0.0821 1 per Kelvin minus 200, oh no, why did I say minus? Times this by 298.15 Kelvin over 1. And so the kelvins will cancel, allowing my Kp to be unitless, which is what we want because Kp is an equilibrium constant. So the last thing I'm going to do is just multiply across. So 0.990 parentheses 0.0821 times that by 298.15 raised to the first power. And that's going to give me a Kp value that's 24.2. And this is going to be my final answer. Okay. All right, so notice that if we express the concentration in partial pressure units, Kp is greater than 1. So if Kp is greater than 1, at equilibrium, we know that there's going to be more reactants than products. And so if more products than reactants, I apologize, let me take that back. So since Kp is greater than 1, then at equilibrium, there's going to be more products than there are reactants. Now, if we express the concentration as molarity, notice that the Kc value is roughly equal to 1. And so the value for Kc and Kp, they do change because the unit is a little bit different. One is in partial pressure and one is in molarity units. And so even though the concentrations, the unit for concentration, they're proportional, so pressure is proportional to concentration, the actual value for Kc and Kp is going to be different. All right, so that's pretty much it for this lecture video. Just please make sure that you guys are only counting the number of moles of gases, not anything else. So if you guys have a heterogeneous equilibria, then you don't count anything that's not gas. You only count moles of gases, and that's it. All right, so that's it for me in this lecture video. Catch you in the next one. Bye.